is Andrea Bevilacqua, from our friendly, well, your friendly institute across the little street, and he will tell us about work about the formation of symmetry.
Okay. Okay, good morning. So what I will talk about is, as the title suggests, k-deformed boost for a two-particle system. And this is based on, these are the three main references that I will use during this talk. Of course, there are several more references, but usually they are contained inside this paper, so I will not talk about them explicitly. So this is, my talk will be divided in three parts. So at the beginning, I will give some motivation. Then I will talk about how to do, how do single particles and antiparticles behave? And to try to understand this, I will first introduce briefly what is k-Minkowski, and then very briefly what kind of action you can build on top of it and what are the fields. Then I will talk about what are the charges for single particles and then one particle states. So this first part is just to give an idea of what are single particles and what we know about them in an explicit model, which is well defined. Then I will talk what about two-particle system. Then I will introduce very loosely what is a Hopf algebra and how we get it from the group. And then I will talk about finite two-particle boosts. So first part, as I said, is one particle. Then here we have two particles. And finally, we will basically apply what we learned from this second part. So now that we have this two-particle boost. So what does it mean concretely? So we will study a simple case, and then I will conclude with some remarks.
May I ask a question?
Yes, of course. Okay, so this is basically the nether charges that you get from the variation of the action. So you take the action, you take the variation. Yes. I will show you. I will not do computations too much because. Yes, I know. But this is what you said. Okay, so some motivation. Of course, this is the more. What everybody talks in this field of work. So we have gravity, we have also quantum mechanics, and a general theory of nature should, of course, naturally encompass both. But of course, there are difficulties because they cannot really be merged directly. For example, time in quantum mechanics is a parameter. In general relativity, it is not because all coordinates are equal. I will not talk too much about this. So what to do? So we can give up, but it's not really satisfactory. We can build a possible model of quantum gravity directly. Of course, there are several approaches to this. You can try string theory, you can try blue quantum gravity, you can try whatever you want. Of course, this depends heavily on the assumptions you decide to make, because you need to kind of solve these problems in some way. Or you can try to find, some physical regime where you can build a potential effective theory of quantum gravity, which does not depend on the details of the final theory, and then study that one. So this is what I will do in this talk. So one such theory is based on k-Minkowski spacetime. We will talk about it a bit in more detail later. And intuitively, this is basically an effective flat spacetime limit of quantum gravity. Now, these limits, as they are just here to give you an idea of what is the physical regime in which we are working, because of course, this stuff are dimensionful, so we cannot really meaningfully send them to zero. But if you want, you can imagine that this is the regime in which k-Minkowski spacetime is defined. So Newton constant goes to zero, h goes to zero, but the ratio remains constant. Physically speaking, more pragmatically, it means that all the lengths involved are much greater than Planck length, but the energy is still of the energy of at the level of the Planck energy. And where kappa is an observer-independent quantity, so this kappa over here. Gn is the Newton constant, Newton gravitational constant. Gravitational constant, yes. Okay.
So kappa has units, or kappa is
kappa? Yes, kappa has units. Kappa has the yes. Units of moment. It's a mass. Yes.
So it's a meter.
1 over meter. Yes, 1 over meter. Yes, 1 over meter. 1 over meter. Yes. Yes. So, So basically now we will show basically from the basics of this model how to build first one particle, and then we will build up to physical predictions. So how do single particles and antiparticles behave? So first of all, what is k-Minkowski spacetime? So k-Minkowski spacetime is a spacetime whose coordinates satisfy this commutational relation, which is the commutational relation defining the AN3 algebra. So here you can also see the dimensions of 1 over kappa, because on the left you have length square, on the right you must have length square. So 1 over kappa is 1 over length. Kappa is 1 over length. Indeed, kappa is 1 over kappa has dimension of length. And this, since this k-deformed theory is intended as an effective theory modeling quantum gravitational effects, it means that in the this 1 over kappa is usually considered of the order of the Planck length. And of course, the formal limit kappa to infinity gives the classical limit. Classical here meaning that if we take this limit over here, the coordinates commute, and we are just in Minkowski. So this is very abstract and very fuzzy. So how do we actually concretely work on this? So the first step is to pick some actual physical, explicit representative of this algebra. So here I wrote this down. And so representative just means that if you use these matrices, they satisfy this algebra over here. And notice that they are dimensionful because of this 1 over kappa in front of them. So what to do? Well, now we have the elements of the algebra. The most natural thing that we can do is build a group on top of it. And the group is basically the exponential of the algebra. Now,
If you should specify what the epsilon are.
Ah, yes, it's true. The epsilon are basically unit vectors. So for example, if this is x1, then epsilon is 1, 0, 0. If this is x2, then the epsilon is 0, 1, 0, and so on. If this is x3, this is 0, 0, 1. So are the unit vectors in the 3 directions. Sorry, I forgot to write it down.
So the notation is that I is the product of -1, and so
I just said I. You could just say, okay, xj is.
Oh, in the base.
Ah, yes. Yes, I know. Sorry, this is my mistake. This
J.
like J, yes. Yes, that's perfectly right. Yes.
Engineers will always
J for the I. Yes. No, sometimes in engineering they use J for the imaginary. Yes. But here this is the complex unit and this is just an index. Sorry for the confusion. So you just take this group. So here are 2 things to notice. First is that since this x0 and x don't commute, we need to choose an order for this.
so for both operators, because
these matrices. No, here by definition the anti-Hermitian, because this is real. For example, this by conjugation you get a minus on top of it. So no, not even anti-Hermitian. No, sorry. I just got it wrong.
Exponential.
Yes. Meaning that when you take the dagger, you get, and you multiply it. Yes.
There's no reality what's in it.
Yes. So this is not easy. But thanks for the question. Yes, I was wrong saying that this is anti-Hermitian because it's not true. I will show you in a minute. So as I was saying, first you need to.
It's like the operators corresponding to the coordinates commute.
Yes.
The only
Yes. Yes. So 2x0 commute, 2xy commute, xy commute, but x0, xy do not commute. So as I said, you need to choose an ordering for the plane waves. We choose this. It doesn't really matter. It's just basically a change of coordinates in momentum space. And notice that since xi and x0 are dimensionful because of this 1 over kappa, then so are ki and k0. So these have the dimensions of momentum. So what do? We have the exponents. We just compute them. So this is just a definition of the exponent of an operator. And these are just simple matrices. So just plug them in. And oops, sorry for this. And when you finish the computation, you get this. Now, here P0, P, and P4 are given by these objects here. I didn't write it explicitly, but also this K is just, this K but you can write it also in terms of this P0, Pi, and P4. And this P bar 4 and P04 can also be written in terms of P0, Pi, and P4. So basically, all the entries in this matrix are uniquely defined as long as you know P0, Pi, and P4. And you can get P0, Pi, and P4 if you act with this matrix on this vector over here. So you just do, and you get this relation here. In other words, basically, these matrices are in one-to-one correspondence with this set of numbers. And this set of numbers, of course, there are 5 of them, but we had 4 coordinates, k high and k0. This means that they must satisfy some trivial relation, and they satisfy this relation over here. So basically, these coordinates show that the manifold corresponding to this group is the de Sitter manifold, which is described by this relation over here. Not the full de Sitter manifold, because this P plus, so P0 plus P4, if you add them up, it must be positive, and also P4 is positive. But so here is basically the first way in which you can show that to non-commutative space-time correspond chord momentum space, if you want. Okay, so as I said, we have now two possible choices for momenta. Either the Ka, the initial Ka, which is called B cross product basis, or the Pa, which is called the classical basis. And they both can be interpreted as coordinates in an intrinsically curved momentum space. But now their sum is non-trivial, of course, because usually when you have a momentum space, you have it without curvature. So you just add momenta component by component. Here we cannot. We just our momentum space is now a curved manifold. It's a group. So how do we go about adding up momenta? We just use the group property. So whenever we multiply 2 elements of the group, we get another element of the group whose momentum is now this deformed sum of momenta. Now, what we do, we just take this, this matrix over here, and do the multiplications. And if you explicitly use this basis, we get these relations for the sum. And if we use the other basis, we use this other relation for the sum. Now, of course, since the sum is deformed, then so is the minus sign, because the minus sign is the inverse of one of the group element is another group element with the antipode of the index. So the antipode of the momentum. Antipode just means minus, deformed minus in this context. And of course, by definition of the antipode, each momentum deformed added to this antipode, regardless of the order, gives 0. To answer your question before, whenever you take the dagger of this, you basically get an antipode inside the momentum. You just
but to answer the question that we come to this point, X0 is our definition, and if I am correct,
these are real. Everything is real. Yes. No, because they are finite. Yes. Yes. This is finite. Yes. Yes. These are 5 by 5 matrices. So yes. Yes. But even this is just okay. Yeah. Sorry. Okay. So, but why P and not K? So why am I talking about 2 possible bases in momentum space? Basically, the reason is that using P, we can work in a commutative space-time, although we have to take care about a few things. So basically, using an object which is called the yield map, one can send elements of the group EK into a canonical plane wave EP. So this is just a relation. And EP is just what you would expect. This is just a canonical plane wave, so what you usually use. But of course, we need to take care, because whenever we have a product of 2 elements, the Weil map sends it to a plane wave, but whose momentum is the deformed sum of momenta in the classical basis. And if we want to now describe this plane wave as a product of 2 plane waves, one with momentum P and the other with momentum Q, we can do it, of course, but we need to introduce a star product, because since this deformed sum is not commutative in general, then neither will be the star product over here. So now, why do we do this? It's not necessary per se, but it makes things much easier because we can work now in a commutative spacetime. And as I said, the star product is in general not commutative. Okay, so basically now we know that we have a star product, we know that we have a commutative spacetime, and we know we can multiply stuff together. So let's just introduce the action directly. So we have two possible actions because we have two possible orderings for the star product, because here we have a dagger. Here I'm talking about a complex scalar field. So basically you can put the dagger either before the star product or after the star product. And the action that we chose is this one. Now this is not a random choice. We have our reasons also with respect to discrete symmetries, but I will not talk about that. But notice, of course, that in the limit kappa to infinity, these two objects are equal. These two objects are equal, and you get a 2 which simplify this 1/2, and you get the canonical complex scalar field action. So how do you compute the equation of motion now, and why do we need them actually? We need the equation of motion because we need to understand what is the mass shell for these particles which are described by this action. So usually one takes integration by parts. Here we do the same, of course, but the issue is that in this case, since we are in the deformed context, the Leibniz rule for derivatives doesn't work. Why? Because you can show it immediately from this. So let's take this object over here. So this is I times the sum of momenta times, this is a canonical plane wave, remember. So this is just a derivative acting on this wave. And this wave is a star product of two waves. Now, if the derivative actually satisfies the Leibniz rule, then this is equal to this plus this, of course. But now this is once again a derivative acting on a canonical plane wave. And so we get this. So if the derivative actually satisfies the Leibniz rule, then the deformed sum must be equal to the canonical sum. And we know it's not true because we showed it already here. So derivative must not satisfy the Leibniz rule. And more complicated rules need to be applied. Here I give an example. So whenever you try to take the time derivative of some product, you get this stuff over here. Now, I will not define what is delta plus here, but in the limit of large kappa, it behaves like kappa. So in the limit of large kappa, this ratio goes to 1, this goes to 1, and this goes to 0. And you're back again to Leibniz rule. So everything works out in the limit. Now, after some computations, you can obtain the equation of motions, and these are just the Klein-Gordon equation of motions for both phi and phi dagger. And any complex field which satisfies this equation of motion can be written in this way, and notice the presence of the antipode here. So this is a crucial point in this whole construction. And of course, you can also explicitate the same equation of motions now in terms of A and A dagger, B and B dagger, and you get the same. So now single particle charges. So what are the charges, and how do we get them? Of course, as I said at the beginning, this is just using the Noether's theorem. So you vary the action, you have a symmetry of your action, you vary it, and you get the charges. The computations are, however, a bit difficult and a bit long, and recall the integration by parts that I just showed you. So basically, only the translation charges are easily obtained in this way. It's not as if you cannot obtain the other charges this way, but this is just the easiest. And this is fine, but I already showed the results. So these are the results. So after some long computations, you get that these are the charges. Now, of course, since we had 5 coordinates in our description of the system, we have 5 charges. And notice this alpha p. So this alpha p is some momentum-dependent function which goes to 1 in the limit kappa to infinity. I will not write it down, but just there. And notice also that this important factor here. So A dagger multiplies minus S of omega, and B dagger B, multiplies omega, and same for spatial momentum. In the limit kappa to infinity, as I was saying, now this alpha goes to 1, and the antipode just goes to canonical minus, so minus omega is just omega, and you get the canonical charges that you get usually in quantum field theory. So in the canonical limit, you get the canonical charges. And notice here that this is the first hint that particles and antiparticles behave differently, but they have the same mass. Why they have the same mass? Well, because they have the same on-share relation, but I will show it more explicitly later. And behave differently because, let's say, A dagger creates particles and B dagger creates antiparticles. From here, we see that the momenta for particles is related to the antipode, and those of antiparticles is not related to the antipode. So how do we show this explicitly? So basically, we just need to build the states which describe A particles, B particles, and then get the eigenvalues after I didn't say it here, after we apply this operator P mu. And we will see that the eigenvalues are different, but they have the same mass. Okay. Okay, so as usual, we define the vacuum as a state which is annihilated by both A and B. And we define the one particle and one antiparticle state as those created by A dagger and B dagger. Now, I really don't know whether this is a particle or this is an antiparticle. The only important thing is that one of them is a particle, the other one is an antiparticle. And now we want to know what do we get whenever we apply P mu to this PA and whenever we apply P mu to this PB. Now, I didn't say it before, but when you compute the action, you compute the variation of the action, one of the things that you can get is the symplectic form. And out of the symplectic form, you can also get the commutational relation of AA dagger and BB dagger. And we computed them and we got this relation over here. So A and B commute, whether dagger or not. And AA dagger and BB dagger have this commutation relation over here. So once again, alpha P goes to 1 in the limit kappa to infinity. So you get, again, the same canonical relations. But now, whenever we apply, let's say, Pi to this QA, so this is Pi, and this is by definition QA. Now, here B and A dagger commute, so this term goes to 0 immediately. Here we have A dagger, and we use this commutator to switch it around. So delta 1 over alpha times delta plus A dagger A. Now, this goes to 0 because applies to 0. And 1 over alpha and alpha go away, and this A dagger creates again a momentum state. So as I said, these A particles, the spatial momentum of it is minus S of Qi. Now, if I do the same thing for B, we do the same exact procedure, but the only difference is that while in the A states, we get minus S of Pi for spatial momentum and minus S of omega for energy, for the B particle, we just get Pi and omega. Of course, minus S of Pi and minus S of omega are positive. Notice that P is different than minus S of P, and the same omega is different than minus S of omega, but you can check that P mu is exactly identically equal to S P mu. And this is true both off and on shell. So in particular, when they are on shell, they are both equal to m squared. So particles and antiparticles do have the same mass, but they have a different momentum. The antipode. S is basically minus in the deformed world. So minus S is basically canonical minus deformed minus omega P. Still, if you apply them both, you get a positive quantity because of how the group is built. But nevertheless, since this deformed minus is not a canonical minus, you get that P is different than minus S of P. Of course, in the limit, the deformed minus S goes to the canonical minus, so you get minus minus, so it works out. So how about boost for one particle states? So for one particle states, everything I showed up to now is basically very easy, and also boosts are very easy. For example, if you take a boost in the x direction, then the particle which is initially at rest, well, is just boosted in the same way. So both A and B particle gets this stuff over here. And once again, you can check what are the momenta, so P0 and P1 in this case, because we have the boost in the x direction. And the A states get minus S of whatever you're computing, and the B states just get the momentum. So, short summary up to now, what do we have? So we have a well-defined model which shows that particles and antiparticles have the same mass, but if one of them has momentum P, the other has momentum minus S of P, and P and minus S of P are different. And single particle states are easily defined, and boost or single particle states behave as usual. So for now, everything works out. What do we need now? Now we need to expand our formalism to include the action of the k-Poincaré algebra to two particle states. So to do this, so what about two particles? We need to understand what is a Hopf algebra and how to get it from the group. Now, what is a Hopf algebra? Here, I change a bit from the abstract that this was sent to everybody. I will not talk about explicitly and technically what is a Hopf algebra, but I will give let's say a super crash course. I will just give an idea of what it is and what it means for us. So a Hopf algebra is basically a structure which consists of both an algebra, a coalgebra, and an antipode. Now, loosely speaking, what is an algebra? An algebra is just what you know. So some generators, some commutators which satisfy the Jacobi identity and everything you already know about algebras. A coalgebra is a bit more complicated and basically describes how the generators of the algebra, which is defined here, act on tensor product of states, basically. So whenever we have, so let's say P, or n. Before we saw how it acts on a single particle state, but what about if we have two particles in a two-particle state? And the antipode, actually, we already met it. It was basically this S, and it encodes basically what it means to have a reverse transformation. Now we'll go a bit more in detail about this. So more on the coproduct. In the undeformed context, the action of infinitesimal generators on two-particle states follow the Leibniz rule. What does it mean? It means that whenever we want to know what is the momentum P mu of a tensor product of states, so we have first that P mu acts on P and not on Q, and then it doesn't act on P, but it does act on Q. And now, of course, this brings out a P, this brings out a Q, and you get the total momentum. But this is just canonical, nothing difficult here. Of course, this kind of Leibniz rule can be described as the action of a trivial coproduct, which is defined this way, on this tensor state. Why? Well, because if you look at this and you apply it to this tensor state, you get exactly P mu, which acts on P, and nothing which acts on Q, plus nothing on P and P mu on Q. So this is in the undeformed context, because you see from the U. Intuitively, we expect that in the deformed context, we'll have basically some different coproduct rule, such that we still get that when we apply it to the tensor product state, we still get the same relation, but of course with a deformed plus. So we expect basically something like here. Now, we already saw that, for example, here I wrote it for the only the zero component, that when we add two momenta for the zero component, the rule is not particularly simple, let's say. And we also recall, I showed you this before, that whenever you act with the derivative, time derivative on a product of stuff, you get this very complicated relation. But now look that this strange complicated relation is actually pretty similar to this object over here. You can see, for example, this partial zero phi is P0, so the first momentum 0. And this delta plus over kappa psi is the second Q, the second particle Q plus over kappa. Again, here you have kappa over P plus for the first particle, and then Q0, you see? And here you have PQ, and then 1 over P plus. You see, so basically this relation, which shows that the action of this operator on this product does not follow the Leibniz rule, is very similar to this, or apparently very similar to this deformed sum, which is also related to the coproduct. So basically, what does it mean? It just means that if we have a coproduct, we expect that the action of the coproduct cannot be Leibnizian, because the coproduct should describe something like this, and this does not satisfy the Leibniz rule. And it is somehow related to the momentum group structure, because, as I said, this is basically the same as this. So this is just not mathematics. This is just to give you an idea of what's going on, of course. You can codify this much more mathematically than this, but you can look at the references for this. So what about the antipode? So in the non-deformed context, everything is easy once again, because the antipode of P mu is minus P mu. And by definition, P mu plus minus P mu, or minus P mu plus P mu is 0. And once again, whenever we take the deformed context, the plus gets deformed, and so does the minus. And once again, remember that we already encountered this S, so this antipode, at the group level. So what I'm saying is that basically there are non-trivial connections between the group structure and the Hopf algebra structure. And we will use the link to obtain the coalgebra of the antipode P mu and the antipode of P mu and the coalgebra of Ni. Now, I don't know if I will have too much time, but I will try to show you some steps because it's interesting. But there are
20 minutes to go.
20 minutes. Okay, so I'll just very briefly skip over this and then we'll see. Well, to get the coproduct and the antipode, basically what you use is this B-cross product coordinate function. This is, you don't use this necessarily, but this makes it much easier. What does this mean? What is this B-cross product coordinate function? You just, whenever you apply it to a group, it takes out the momentum component of it. And you can define the coproduct of F on two group elements in this way. This is the Wydział notation. We will talk about it later. And of course, the antipode is the F of G to the -1. So what do we need? We just need the product of two group elements and an inverse of a group element. Now, I maybe skip this. What is important to know is just the result. So the product of this plane of these group elements is just this object here in the B-cross product basis. And the inverse is just this. So whenever we apply now, we want the coproduct of F0, let's say. So this is defined as F0 on the product of two plane waves, but we already computed the product. And now this just brings down this K0 plus Q0. But now K0 plus Q0, we can describe it this way. Why? Well, because this F0 brings down K0 from here, and this 1 does nothing here. And this 1 does nothing here. And this F0 brings down Q0 from here. So this is this. And you see that we have recovered some kind of coproduct. So as an object, which can act on a product of states, not yet states, but you get the point. So for spatial components, it goes exactly the same way. So here you have the product, and this brings down the spatial part. And once again, you have this non-trivial coproduct over here. So this Fi acting here brings down K. 1 does nothing. And then this object here acting here brings down K. And this F brings down Q. For the antipode, I will not repeat, but you get basically exactly the same thing. You put inside the e to the -1 and then bring down the necessary component. So basically, abusing a bit of notation, this is what you find in the literature. So whenever you have a product of stuff, now I'm not being very precise here. So these have been defined when you apply them to a product of two group elements, but this work also on tensor product of states. So you have here the coproduct and here the antipode. And notice that the only thing that we needed was the group structure and then some function acting on it. So for boosts and rotations, how do we get them? Basically, the key observation is that AN3, so is our momentum manifold. This is the Sitter manifold that I showed you before. And if we want to have some action of boost SO13 on it, we need to find a way to do so. And the key observation is that they are both subgroups of SO14. And one can use the Iwasawa decomposition, which is written in this way. So SO13 is, of course, the algebra of SO13. And A and N are generated by X0 and Xi, respectively. So what does this mean? Practically speaking, whenever we exponentiate this, elements belonging to this will give us the group elements, so the plane waves. And these are the boosts and rotations. In other words, because of the Iwasawa decomposition, whenever we have an element on SO14, then given some boost or rotation and some G, so some group element, then there is a unique element K prime and a unique G prime such that this holds. Why is this important? Because if you apply now the inverse matrix here, we get the transformed plane wave. Okay, so basically this is what we need to understand what is the boost. Now I'm not still talking about the coproduct, but I will talk about it in a while. So we are only interested, let's say, in infinitesimal boost transformation. So we just expand this. The key point here is the matrix over here. Now this matrix here is momentum dependent in general. And the momentum dependence, of course, is such that in the limit kappa to infinity, it goes away, and everything works out fine. So here, for example, this Kg is this. So this is K times G is equal to G prime times K prime. And notice that here, this K prime has a bunch of parameters that we need to find out and to determine. So what do? We just do the product on the left-hand side, the product on the right-hand side, and match the components and find out what are these parameters. And once you do, this is the K prime that you get for a boost in direction 1. So what about the coproduct? So as I said, for the coproduct, as I said before, it's basically related to the product of group elements. So here we also need some boost or Lorentz transformation of a product of two elements of the group. So this by definition is Kg. Now here it should be just GH and then K prime G to the -1, but we can insert this product over here because it's 1. Now, what about this? We have Kg, we have K prime G, it's over here. So the inverse, you can get it if you need it. What about this? The surprising answer is that this is completely irrelevant for the definition of boost and rotation in our case. Why? Well, because basically a multiplication from the right of a matrix like this does not affect coordinates. Remember, the coordinates are in the last column of the group elements. And a transformation like this has 0 everywhere on the last column and row, except the 1 here in the last corner. So whenever you multiply this from the right, this column is unaffected. So what does it mean? It just means that we can define a boost for a product of states. It was this way, of course, but what we actually need to compute is just this object here. So we can forget about this. And now k prime, we have it, so we can just compute it. So we can do this compute this object here explicitly at first order in the parameter C. And this is what we get. And once again, if you work as we did before, you can get the coproduct. Once again, you can read it off from here, basically. So you see, this is n acting on G times nothing on H, plus this object acting on G on the first, and n1 on n on H, and then this epsilon and this object acting on G, and then m on H. So you can read it off immediately. And this is the correct coproduct. And you just get it whenever you multiply elements of a group, and you appropriately define Lorentz transformation on it. Now, another short summary. So we can basically deduce the action of generators on tensor product states from the group structure. However, because we have basically two different coordinates, here I talked about one coordinate at a time, but you can get, of course, because both the coproduct and the antipode in both bases whenever you need. The only important thing to remember is that, okay, I'll write this over here. Basically, you can get both the algebra and the co-algebra in whatever basis you like. But sometimes, for example, in the classical basis, the algebra is non-deformed, but the co-algebra can be tricky sometimes. In the big cross product basis, maybe some part of the algebra is a bit more ugly, but you get much easier coproducts on the other side. So basically, you can do whatever you want with either big cross product or classical basis, but the deformation does not go away even if you simplify the algebra. You just get transferred to the co-algebra and vice versa. So the kappa deformation manifests itself at the Hopf algebra level, and we may choose a basis such that the algebra or the co-algebra are easy to work with. But once you introduce a deformation, it does not go away. And algebra, co-algebra, and antipode are all related to the momentum group. So what do we need to get at this point? We just need a two-particle finite boost. And how do we get it? The same way. We have the Iwasawa decomposition. This time, this is a finite boost, again in the x direction, but this is what we do. And this is just a full matrix without any expansion at first order. And you just do the computations. Now, to simplify things, we can take this matrix and expand it at first order in 1 over kappa. So this is this matrix L prime tilde, and L prime for k which goes to infinity is the same undeformed one. And you can also explicitly check that they satisfy the requirement for a Lorentz transformation. Okay, so now, just to be explicitly clear, how do we act with a coproduct on a tensor product state? As I said before, since multiplication from the right is irrelevant, only the matrix acting from the left is the relevant one. So whenever we have this product over here, only L acts on G, and only L prime G acts on H. And now we have both matrices. So now we can compute the finite boost of a two-particle state. Oops, sorry.
No, sorry.
Yes.
What are you asking here? Or the natural?
No, this is a natural definition because it follows from here, basically. Yes, this kg, see this k minus 1, k prime g minus 1. Yes, this is 1. So this is just yes, and this is irrelevant. So okay, and so you get
okay. So you're boosting the first.
Yes, and then boosting the second with this L prime G. Here there should be this, if you want, L minus L prime minus 1. Yeah, maybe it wasn't.
L G L prime G minus 1.
Yes, but since multiplication from the right is irrelevant, then we forget about it. And but here this
still that should be L.
Yes. LG prime minus 1. No, okay. I didn't use the subscript over here. Yes, sorry. I forgot to add the subscript. But yes, there should be, yes.
No, because we use the convention.
Yeah. Yeah, I know. But to keep it consistent, I should have added LG. Yes, previous part I added it. So to be consistent, I should have added this LG over here just to make it clear. But since this is the canonical boost, I didn't write anything. So perfect. Now we have the finite two-particle boost. So what do? We use it to study basically the consequence of a finite boost on a two-particle system. So we will study basically the decay of one particle into a particle and the particle pair, at first in the center of mass frame, and then we will boost the tensor product state and see what happens. So this is what we do. Consider a decay of a particle of mass big M, originated at rest, into two particles of mass small m. Now, from the conservation of energy at first order in 1 over kappa and momenta at first order in 1 over kappa, these are the relations that we have. And by conservation of energy, we need to impose that this is equal to m. And by conservation of momentum, this should be 0. Now, from here, we immediately get that P and Q point in opposite directions, because here you see Pi multiplies an object plus Qi is equal to 0. So we can simplify a bit. Okay, we can simplify the problem a bit. We can align them, for example, without loss of generality in the x direction. So the previous direction, the previous equations are exactly the same. It's just now it's simpler to work with them. And we just need to find what is this P and what is this Q, such that these two relations hold. And you just do some algebra, or you put them inside Mathematica, and this is what you get. So Q is basically equal to this object, and P is equal to this other object. Of course, another solution is when Q is equal to this, and P is equal to this, but it doesn't matter. You just switch them around. And notice, of course, that in the limit kappa to infinity, this and this go to 0, and they are equal and opposite as they should. So in the central mass, everything is easy, everything works fine. Now, we can now boost the two particles. We boost in the x direction because this is the boost that we computed before. And we consider, to simplify things, spherical coordinates with the polar axis oriented along the x-axis. So it's easy to work with the formalism. So this means that P mu and Q mu is now this object here. And now we have two possibilities. Now, what is the tensor product states? Can either be PQ or QP. So it depends on which particle you decide to put before. In other words, you can either act with the canonical boost on P and with the deformed boost on Q, or vice versa, of course. Now, the second case can be obtained from the first one simply by switching P and Q. So we just consider the first one, but the second one is exactly the same. You just switch them around. Now, this is the most interesting part, I think, of the whole talk. Now, this is a picture which represents momentum distribution in the center of mass. Now, the red shell over here is the distribution where neither P nor Q are deformed. So this is canonical decay into two particles. And of course, since each direction is the same, they have a uniform distribution on the whole sphere. So you get a sphere for momentum distribution. And this green and blue shell represents the angular distribution of the deformed P and the deformed Q in the center of mass. Now, I need to give some numbers to make you appreciate this figure. So here we chose M equals to 10 GeV. So this is the mass of the decaying particles. The small m is 0.1 GeV. So this is the mass of the decaying products. And notice the incredibly small kappa. So kappa is 100 GeV, which of course doesn't make sense. This, as I said at the beginning, this should be of the order of Planck energy. So it should be enormous. But if we actually put the correct kappa, we couldn't see anything by eye in the graphs. So we just chose a different kappa just to show what happens qualitatively. And of course, it's not possible to see it from this picture, but although they live in different shells, the deformed P and the deformed Q are opposite to each other. So whenever you have a P in one direction, the Q is exactly in the other direction. And to give a more concrete example, so if an undeformed momentum here is 5 GeV, then the modulus of P is 5.12 GeV, and that of Q is 5.37 GeV. Now comes the fun part, because now we boost. Okay, what happens when we boost? When we boost, we have our nice sphere in momentum distribution, and we add to each momentum the momentum given by the boost. So you're moving with certain speed, so particle naturally gain momentum in the other direction. So basically you get some elongated shape over here, but the transversal direction do not gain momentum in the transversal direction. They only gain momentum towards the boost. Now here we chose a boost gamma equals 5, so it's not such a large boost, but notice the very interesting part. So the red cigar over here is what you get when you take the normal particles without deformation and you just boost them without deformation. So this is what you expect the distribution of momenta to be. The green shell is the P particle, which remember the deformed P, so it gets a deformation in the center of mass, but boosted canonically. So if you see, it's basically the same as the undeformed boost, just a bit larger. Maybe you can see it from here. It's a bit larger because it was a bit large. Oops, it was a bit larger already in the center of mass. Here we are just boosting, so nothing particularly strange happens here. But notice the blue part now. Now the blue part is the deformed Q, but deformed boosted. If you remember, this Q gets boosted with this L prime G. And notice that it is dramatically different from the other two. So not only the boost in the x direction, the form act switches the momentum in the x direction, but you also get an angular distribution. As you see here is a bit fatter if you want, and rounder, and here is a bit pointier. So you get an angular non-trivial angular distribution when you take a deformed boost or deformed particle, and you also get a shift in momentum space. Now you can ask what happens to the figure if you switch P and Q, because after all you can. Nothing basically happens, at least nothing visible. You get some small changes in coefficients, but the qualitative effect is exactly the same. And of course here the effect is exaggerated by the fact that you have K equals to 100 GeV, but the qualitative effect is still there. Okay, so conclusions. What can we do with this? So one thing that we can do is, of course, try to find some experiment in which such contribution to deformation are more easily measured. You can do this in several ways. You can try to take lifetime of decaying particles, which are different in a boosted frame, but I will not talk too much about this. And I think this is more important than this, in my opinion. But basically the same process here. Now we know how to use two-particle boosts. But now that we know how to do the two-particle boost, we can just do the n-particle boost, because we just take n, the product of n group elements, and then we boost this product and see what happens. But now what happens indeed? Because we already saw that the second particle is dramatically different from the first one. So what happens if I now add a third? What happens if I now add a fourth? And what happens if I now have 2,000 particles for a whole big object? Does this object get teared apart? What happens? This is not clear. And we haven't started working on this, but it is a quite interesting question to ponder about. So that's it. Thank you very much.
Okay. Some questions. Traditionally, I can ask some people from who are connected. Do you have any question?
Wojtek doesn't have any question.
So perhaps someone have from the audience.
Yeah.
You have a question.
Yeah. So what's really happening? I don't understand. First of all, I don't understand the graph. You said that's the onion-like thing.
The onion-like thing is basically whenever you have, imagine at the center of this onion there is the decaying particles.
So I have two particles. Okay?
No, you have one particle at the center of this sphere, and then it decays in two particles.
Decay.
Decay, yes, these are the decay products.
I thought there was the
No, just a decay. At this moment, it's just a decay. And whenever you have a decay, of course, the particles move randomly in whatever they. So how many particles go in which direction? Here is uniform distribution. So you just get a sphere.
So this is actually the moment.
So I have to imagine a full red sphere.
Yes. Sorry.
So the effect, no.
Yes.
So the effect of the deformation is to make some regions of the parameter space not allowed. No.
No, here I just maybe I didn't
Okay,
say.
so that the red is undeformed.
Red is undeformed.
That's classical thematic.
Yes.
Standard thematic.
Yes.
Now-
Then green and blue, I cut them up just so that you can see the red inside. And I also cut them up so you can see the. Yes, sorry. Yes. No, but in the paper I actually say that the phi in this graph, the range of phi is different. Here I forgot to mention it. So here basically we have three balls, one inside the other, and I just cut the largest one and then the middle one.
So the only effect is to make the modulus
Yes.
bigger.
In the center of mass.
Right. So, but I don't understand now the sorry.
No.
The point.
This is the point. Yes.
But look back again. So what
Yes.
do you mean by non-deformed, deformed Q or deformed V? Like, the information is there, the information for everybody.
Yes, but basically here we are comparing. Basically, what you want to say is you have the formation and you want to see what are the experimental signature of the formation. So you compare with the undeformed case.
No, I understand. But what is deformed Q?
So the form Q and the form P is
They have to be deformed both.
yes. Yes. Both of them are deformed, but in the graph they don't coincide with the same line because they both have a different modulus. You see. So maybe I can.
So they say again, it's very low.
No, okay, so let me.
They're both deformed.
Yes.
Yeah.
So what do you mean in the graph that you have?
No. Hold on. This is extremely simple. Suppose I have a in the center of this picture, I have a part of this. In the case of the part. The red, could you show the picture?
Yes. Sure.
The red is a sphere. So
The red is here, and the possible in momentum space. And the possible momentum of this space are by total point of the red sphere. In the default case, you have a green sphere for P and a blue sphere for Q. And the result of the K are on a total point 1 and Q, one on green, another on blue.
So yeah, the modulus.
Yes, the model is different. So whenever you do.
But they are on opposite direction.
Yes. So whenever you make an angular distribution, you get two spheres. One, let's say this is P, and this is Q.
Okay.
So whenever you do the angular distribution, you get two spheres, one for P and one for Q.
So the green shouldn't, let's say, be inside the red? No.
No, the green is outside the red. This is, you cannot see here, but maybe you see from here. The green is slightly outside the red. And the blue is slightly outside the green. This is very difficult to see with but these parameters are those that show it best.
But you have the value of.
Yes, we have. You brought it here.
So say the model is 537.
And then now it's a question. Now you boost them, of course. And now, whenever you boost,
it becomes an ellipse.
Yes.
In the standard case.
Yes, exactly. So it becomes, in the standard case, is this red stuff over here. Now, P was deformed here, but we're boosting with a canonical boost. So it's still an ellipse, just a bit larger, like it was before. But Q, we are boosting with a deformed boost. So it's not just a larger ellipse. Is this strange ellipse, which is pointier here, fatter here, and a bit behind the others.
Kind of the blue.
So physically what that.
Physically, it means that whenever you find the distribution of momenta in a scattering, so usually you get.
Yeah, like in terms of like arrows, like this.
In terms of arrows.
And what happens?
So basically, here in a boost, you have this this decay, and let's say after a boost, both of them gets this boost, this component, let's say. Now, in this case, in the deformed, they're already different here. And after a boost, let's say Q and P, after a boost, P gets, let's say this, P, but Q gets a different stuff. So this is okay, boost. This is boost. And this stuff depends on the direction. So modify depends on the direction which Q is at the beginning. So the two particles and not particles and antiparticles, but the first and second in a tensor product get a different boost. Of course, this begs the question, can you actually measure what is the first and the second in a tensor product? No, you cannot. Yes, which is why here the most interesting part would be to actually use some kind of symmetric and antisymmetric states. But you and Jurek actually published this paper on the symmetric and antisymmetric, yes? Yes, which is problematic, and you have to use braiding. But then when you use braiding, you can do it. But here, I really don't know what's going on.
No, but the experimental setup is pretty simple, right? I mean, you have a bunch of very energetic particles that decay inside your detector, right? And now, if you have very many events, you can actually reconstruct the angular distribution.
You should play my lithography.
Yes.
So if you look at this picture, the green and blue is certainly much different than the red.
Than the red, yes.
So if you have sufficiently many events and sufficiently sufficient resolution, the detector you actually can measure the difference. So that's essentially the point of this equation. Okay, good. Some more questions? Then thanks the speaker again.
Okay.